if you are okay with it. So welcome everyone to this last session of the semester in our course. Let me share my screen for a little while. I'm really honored of having Professor Hamed Badihi with us. I met him in 2012. We were sharing a laboratory space in Concordia University during a year, and also we were able to work in a common research paper, and since then we have been cooperating in some common research objectives. I'm going to read really briefly among everything Hamed has been doing and has achieved during his career. And mainly he received the PhD degree in mechanical engineering from Concordia University there in Canada in 2016. He was a Horizon postdoctoral fellow with Concordia University for 2 years. And now currently he's an associate professor with the College of Automation Engineering, Nanjing University of Aeronautics and Astronautics in Nanjing, China. Actually for Hamed now, it is June 2nd, Thursday morning, 7:08. So thank you for joining us really soon in your morning. His research interests include all aspects of condition monitoring, fault diagnosis and prognosis, and fault-tolerant and cyber attack resilient control of cyber physical renewable energy systems. His specific research areas include wind turbines and wind farms, solar photovoltaic systems, microgrids, and smart grids. Also, Dr. Badihi is a member of the technical and program committees of various international conferences. He has been serving as guest editor and reviewer of several journals and conferences. So thank you once again, Hamed, for accepting our invitation for giving of lecturing this last session of this course. We are on your hands. Feel free to share any material you like. And thank you once again.
Thank you very much. It's a pleasure being with all of you, and thanks for the invitation actually. So just a moment, I share my screen with you. Can you see my screen?
Yeah, yes, we are able to see.
Great. So I just get everything's ready, and then we are good to go. Okay, great. All right. Once again, hello everyone, and welcome to this last session of your course. It's an honor to be with you all, and actually, it's just like for this presentation, I'm going to go over like some overview. So apparently, we are not going to go into like a lot of details of this topic, that is fault-tolerant control. But I am going to talk a little bit about the methods in general, the applications, and give you some examples and get you familiar with this area of research, right? And the importance of it. Well, I'm happy that Dr. Ismail already helped me with the introduction, so I don't need to go over everything. I had 2 slides to introduce myself a little bit. I am actually currently in China. So you see in this slide just some pictures of the campus that I work at. And also the university has 3 campuses. This is one of the campuses that my college is located in. And you see also the Nanjing downtown, and also Nanjing Confucius Temple, that is like a heritage place in Nanjing. Well, it's a nice town. It would be nice if one day you can have a visit. It's definitely worth it, I think. Good. So I also, I'm happy that you already introduced the research area that I work on. Recently, I have been expanding my research to the cyber aspect of renewable energies as well. So I am more also working on the areas related to cyber security and cyber resilience of renewable energy systems that we're going to talk a little bit on this at the end of this presentation also, if time allows. All right, so for the outline of this presentation, I'm going to firstly talk about safety critical systems, because I believe that first we need to understand what kind of systems are actually the target systems for this area of research, I mean fault-tolerant control, because we need to know what is the main application and motivation to develop fault-tolerant control. And then I'm going to bring you some terminology and definitions that helps us actually to follow the content that comes in the next slides. I'm gonna classify some faults that the important faults that we need to know, and we need to classify different types of faults depending on their location, their behavior. And then we try to model these faults and see how the modeling of faults work, because of course, when you want to design a solution to detect and actually handle the fault effects, we need to model those first. And also we are going to talk about redundancy and fault tolerance. Well, you will see that redundancy is an important prerequisite to fault tolerance, and they are like integrated topics, right? So we need to first understand redundancy very well, and then we can introduce the fault tolerance in an appropriate way with respect to redundancy. Well, we need also to discuss a little bit about fault diagnosis and lifetime prognosis. Of course, this is by itself an area of research, very large area of research, but it is good to have an idea of what it is, because they are very important and very useful for fault-tolerant control as well. So some types of fault-tolerant control really employ the information that comes from fault diagnosis and lifetime prognosis, right? So we need to understand these two functionalities as well. And at the ending part of the lecture or presentation, we're gonna go over fault-tolerant control, and I'm gonna introduce you with passive and active approaches for fault-tolerant control, and bring you some examples, okay, case studies that I believe they are like not too complicated. They are like just generally simple examples that give you like an idea how we can in practice design this kind of systems. All right, good. So let's begin with the definition of safety critical systems. Well, as the name suggests us, safety critical systems are those kinds of systems that the safety is very important in those systems, right? And their failure could result in loss of life, significant property damage, or damage to the environment. And apparently, it's very, very important for us to avoid the failure in these systems, right? Very good examples of these systems, such as aerospace systems, transportation systems, recently self-driving cars, and also medical devices, energy and power systems. These are very, very important applications that actually we call them safety critical systems. All right, so as you see in this slide here, basically any fault this kind in these systems, if they are not detected, diagnosed, and handled in a timely and appropriate manner, they're gonna propagate and finally lead to failure, right? So we need to avoid that, and we need to find meaningful and effective solutions that avoids the propagation of faults to failures and development of faults to failures, right? So we don't want failure. Good. Now with this slide, you might ask yourself, what is the difference between fault and failure? Because in this area of research, we really need to understand this difference, because we are going to work with faults, and we are going to avoid failures, right? So that's why I begin the definitions and terminology with this slide that brings us the important information about how different these topics are. Well, actually, we inevitably we have to deal with different situations in practical and industrial applications. We definitely we deal with specification mistakes when you are designing the components of a system, implementation mistakes when you are implementing those components inside the system, the component defects during the manufacturing of these components from different vendors, it's like possible. And also when the system is implemented and working, we have to deal with real life external disturbances, right? So all these factors actually cause faults, all right? And these faults can happen in either hardware part of the system or part of the system, or both, right? So these faults are inevitable during the life cycle of a system. And when these faults happen, they cause errors. And errors are basically the deviation from the normal behavior or operation of the system, all right? So these errors that happen and actually are evolved in the system after faults in the system can be very useful and actually very valuable symptoms that gives us an idea that something's going wrong, right, in our system. So if we don't care about these errors and let the system continue working, finally these faults would propagate and develop and finally lead to failures of the components of the system and final failure of the entire system, all right? So as you see in this slide, the concept of fault, error, and failure, these are different concepts. And these are, even though they are integrated, they are different. So we need to understand that, okay, particularly the most important point is that fault and failure are different concepts. And basically, if you don't detect and handle the fault effects in the timely manner, they're gonna propagate in your system, develop in your system, and finally fail your system, all right? Now let's have a few more definitions before we go forward. These are the tools that we need to keep in mind when we continue this topic. Well, the first definition in this slide that we have is fault detection. Well, it is very simple definition. It is just detecting fault or faults in a system after their occurrence, right? And basically, apparently, you cannot detect a fault before it happens, right? So when it happens, you need to detect this. And fault detection is this process. And basically, you use those error effects that I already explained in the previous slide to understand that something's going wrong and you can detect the fault in the system. Now, what is fault isolation? Fault isolation is actually determining the type and location of the fault in the system. And normally this happens after detection. So you develop a fault detection system, and this fault detection system detects the fault based on those errors. And then it determines the type of fault and location of the fault, if it's in the sensor, if it's in the actuator, if it's in other components, right? Sometimes, depending on the solution that you develop, it is possible that it happens at the same time with detection. So it is possible that you can have some solutions that does the fault isolation at the same time with fault detection. And then we have fault identification. Fault identification is to determine the magnitude and dynamic behavior of a fault after its isolation. So it's better to say estimate, basically, because you never can perfectly get the complete information for actually magnitude and dynamic behavior of the fault. But you can estimate how it is going on and how it is developing in the system. Good. So the other important definition that we have is fault diagnosis. Fault diagnosis actually is a general concept. So when you say fault diagnosis as an expression, technical expression, it refers to the fact of fault isolation and identification together, right? So that's why some people just simply say fault diagnosis instead of saying fault isolation and identification, okay? And the usual commonly accepted like expression for this like fault detection and diagnosis is fault detection and diagnosis, that is FDD. We're going to talk about that more in the coming slides. Well, then we have fault accommodation. That is another important definition. And it just refers to the fact that you handle the effects of the fault. Okay, so you detect the fault, you isolate, identify the fault, and then using appropriate tools such as fault-tolerant control, you try to handle the effects of the faults after their occurrence, right? And you have to accept the fact that the system is faulty. So you cannot expect a faulty system to work like perfect, right? Because it is faulty. So you have to accept a graceful degradation of the performance in your system, but you handle the effects of faults and you extend the lifetime of your system before it fails, okay? And this apparently gives us valuable possibility for planning of service and maintenance, right? So like technically we say it increases the availability or uptime of the system. And lastly, we have prognosis, that is estimating the time to failure. So it is apparently just the English meaning. So you estimate the time that, let's say, the system becomes faulty, then you estimate how much time I have in terms of operation hours or cycles that the system gets failed, right? That is very, very useful for maintenance, planning the maintenance, right? So these are the important definitions that we need to keep in mind. And the other important information and definition that is, I believe it is maybe one before the last one. This is called failure mode and effects analysis. Why this is important? Because this helps us to plan, or better to say, we actually formulate our detection and accommodation or handling of the fault in the system, right? Because you need to have a knowledge about these faults. And this happens actually in failure mode and effects analysis. Well, it is the process to identify and fully understand the potential failure modes and their causes in the system. And particularly in this process, we try to answer three important questions. The first question is, what are the possible component faults? Okay, so you determine what are those component faults and possible faults that may happen in the system. If you're dealing with a wind turbine, for example, it can be pitch actuator fault, it can be pitch sensor fault, generator fault, rotor blade icing, and etc. Okay, so you determine all these. And also you determine how often they may happen. This can be obtained by industrial evaluations and surveys that you do in the industry. And also you need to ask how they propagate through the system and their effects on the surrounding environment, how it is, yeah? So we need to determine all these. And based on that, these two first questions talks about basically the severity and occurrence frequency of the faults, right? So therefore you can refer to such a plot, and basically a fault that happens frequently and also with high severity, that's a very, very critical fault, right? So it gets a specific rank. And basically you're gonna rank your fault modes based on their severity and the occurrence frequency in the system. Good. So you're gonna come up with such a list that it has different categories. Let's say here we have, let's say 3 different categories: less severe, severe, and most severe, right? And then you list all these possible faults. And then you ask from yourself, okay, how I can handle this situation, how I can address this problem. And basically the objective of FMEA is to introduce the effective schemes or strategies for data acquisition, that is system monitoring, and system redundancy for actually in the structure of the system that we can handle the fault effects if they happen. So based on the FMEA, you can introduce appropriate sensors that you need in the system, or like other methods of like evaluating the health condition of the system. It can be, let's say, vibration monitoring, strain monitoring, machine vision using UAVs around the wind turbine, that if, let's say, the blades are broken or whatever, or there is ice on the blades or so on. And also you can determine what redundancies in terms of hardware or analytical, that I will talk about in the coming slides, you can use in the system to accommodate the effects of these faults if they happen. All right, so FMEA is very, very important. It's the knowledge base for your design. Good. So the last important definition that I have for you is health management. Health management is actually the complete package. Okay, what I mean by complete package is basically you start from FMEA that I explained in the previous slide, and then using that, you come up with the appropriate strategies for monitoring of the system and meaningful solutions for fault detection and diagnosis, which is FDD. So just please keep in mind, FDD stands for fault detection and diagnosis. We will use this frequently in the coming slides. Well, the information from FDD can be used for like enabling a meaningful lifetime prognosis, because when the fault has happened, we need to understand how long time is left for us before the system fails. And this gives us remaining useful life, or RUL. This is another important expression, RUL. RUL prediction. And then using FDD information and what I call lifetime prognosis LTP information, you can have actually planning for your operation and maintenance, which is O&M. And you can realize condition-based maintenance instead of time-based maintenance. So usually in industry, people use time-based maintenance. That is very costly. You just, let's say every month you service some parts of your system and you replace the parts that they need to be replaced, regardless of their condition, like real-time condition. I mean, like maybe the part can work a few more days or months, but you change it just to be safe. And that is costly. But if you realize FDD and LTP, you can come up with condition-based maintenance. That is the most optimal way of the maintenance and service. And based on the condition of the system, true condition of the system, then you pinpoint those parts that they need to be changed, and you actually do the service, right? So you can save a lot of money, particularly, let's say, in the systems that faults are very frequent in them. Good. Now, there is one important part to this, this sketch that I have here, and that is actually fault-tolerant control, the topic of today's lecture. And this fault-tolerant control, or FTC, basically employs the information from FDD and LTP to enable an advanced level of control that can accommodate the effects of faults after they're happening, right? So you use the information, FDD information and LTP information, to leverage the control that you have on the system, and you expand the time that you have actually until the system really needs to be serviced. All right, so you can expand that actually service time of the system, and you can expand the availability of your system. That's why fault-tolerant control is critically important. Great. So this is a very useful sketch for you that you can refer to whenever you want to understand, okay, what is the relationship between FDD, LTP, and FTC. Just keep in mind that basically LTP is a more advanced topic, and unfortunately there is not as many studies as you see, let's say, on FDD and FTC, but it is very, very important, and it is the future of this field. So if you're interested to work in this field, I would suggest that you have more studies on prognosis as well. All right, let's continue. Now we have enough background knowledge that we can a little bit go deeper in this topic and we classify actually the faults now. All right, the faults can be classified based on their physical locations or based on their time characteristics. So there are two different approaches for fault classification. If you classify the faults based on physical location, they may happen actually in sensors, in actuators of the system, or in the plant or process, main plant or process of the system. You may have other components here as well. That's why we call sometimes process faults as component faults. Well, even faults, even though it's not shown here, maybe the faults may happen even in the controller part. And we hope that it doesn't happen. Otherwise, that would be very critical and very difficult to address, even though there are some recent studies on this aspect as well. All right, this is about the physical location-based classification. And the other method that we can use for classification is time characteristics of the fault. So we look at the dynamic behavior of the fault. If it happens abruptly, or if it happens incipiently, meaning that it gradually starts from zero and it increases in its severity or magnitude. And either also it's important to see if the fault is permanent fault, meaning when it happens, it continues until the end of failure, or it is intermittent, meaning that it comes and goes, right? It is also possible. So these are different time characteristics that actually you can classify your fault based on these characteristics. And if you study fault diagnosis and fault-tolerant control, you would see that incipient faults are more difficult to be detected and sometimes even for accommodation after detection. Good. Just to give you some examples, real life examples of faults. Here you see a wind turbine. Most of my examples are about wind turbines in this lecture because firstly, it's my own main direction of research. And second is that wind turbines are they are excellent examples actually for fault detection and diagnosis and fault accommodation, because they are very integrated systems and they include both electrical and mechanical components, and a very good platform to learn this area of research in general. So that's good to take it as a reference and bring our examples on. All right, in this slide, as you see, we have generators, let's say in the generator part of the turbine, we may have a sensor fault, generator speed sensor fault, that based on industry evaluations, it's mostly type of scaled measurement in the in the form of a scaled measurement, meaning that the measurement becomes scaled, let's say by 0.85 or whatever that may happen. And we may have also actuator fault in the generator in the form of torque actuator offset, right? And we have also the possibilities for faults in the pitch system. You may have blade pitch sensor fault. And normally this is mostly the case of stock measurement, meaning that your measurement all of a sudden gets stuck, let's say at 5 degrees. You see that your sensor measurement is just like 5 degrees all the time. The other case is blade pitch actuator fault that is usually in the form of loss of effectiveness, because you know these blades are changed in the pitch angle or regulated in the pitch angle by these blade pitch actuators, and it happens like frequently during its operation of the wind turbine to control the wind turbine. And usually the effectiveness of the blade pitch system actually reduces over time. So instead of 100% effectiveness, it becomes 85, 50, and finally fails, right? So this is another case that we have. And in the case of component fault, I can give you an example about rotor blade icing or debris buildup fault. This changes actually the rotor aerodynamics and reduces the power of the turbine. So this is a kind of system fault. It's not sensor or actuator fault. It is a kind of system process fault, right? So these are different real life faults that you would see actually in a wind turbine, beside many other faults that may happen in a wind turbine. All right. Now let's have a look on the modeling of the faults, how we can model these faults. Well, let me just have a little bit of water, sorry. Okay, so for the modeling of the faults, firstly, like any other dynamic system, you can develop the models, either input-output models like transfer functions, ARMA models, or you can develop in the framework of state space, right? So these are two possibilities for modeling the faults. And in the next slide, I give you the example of state space models, how they look like when you model the faults. There are two types of representations for the faults. They can be either represented as additive faults, that they get added to the signals, and they may happen in the form of multiplicative faults, right? They multiply. And time behavior of faults can be, as mentioned before, abrupt faults. They look like stepwise change in the signal, and they may happen in the form of incipient or gradual faults. Well, regarding this severity of these faults, they may be partial faults. Just remember the actuator fault that I gave you in the previous example. The actuator can get like 80% effective, 75%, and so on, whatever arbitrary number, right? So as long as this is not 100% loss, we call it partial fault. And if it goes to 100%, it becomes total or complete failure. And we may have stuck or frozen fault, like stuck measurement of pitch angle in a wind turbine, and floating faults that the name suggests, like they arbitrary change and by themselves, and like it's just how it is, you know, it is like a real life system. The fault may look like differently. Okay, so here we have an example. As you see, normal system state space model is shown here. So I assume you are already familiar with this because this is our last lecture of this course. So I assume that you already know how state space model looks like. You have system matrix, input matrix, output matrix, and here the feed-forward matrix is not shown anyways, but this is like for the normal model. And when I say normal, I'm referring to the fault-free scenario. So you have a system that is completely healthy, and it is the topic of conventional control. So this is the state space model in that case. But if fault happens in the system, that may happen, as mentioned, in the actuator, sensors for input sensors, output sensors, or the process fault, or even the controller fault. Yeah. So when you consider all these, you can modify this state space expression to the faulty expression that is shown here. And if you pay attention, you would see that how we can, let's say, get the representation of the faults. Let's say output, as you see, let's say this fault is Fy, that is basically the output sensor fault vector, and you can simply add it to the output part of the state space model, right? And similarly for other things. So this is a way that we can model these faults. All right, just it was an example to give you an idea how we can model the faults. And then you're gonna study this model instead of the normal model. All right, now let's talk about the important topic of redundancy. It is very important because redundancy is prerequisite of fault tolerance. And basically, you may have hardware redundancy or analytical redundancy. Well, what is hardware redundancy? Hardware redundancy is just like for the same function inside a system. For example, measuring the pitch angle in a wind turbine, you use more than one sensor. That would be hardware redundancy. And that is apparently very costly because you have to use more hardware than necessary. But the good thing is just in case if one of them fails, the others can take on the responsibility. What is analytical redundancy? It's an alternative to hardware redundancy, meaning that instead of using real hardware beside like your sensor, instead of using another sensors for one sensor, I mean more than one sensor, you use actually a model of that sensor. And basically, you use a software that can model the behavior of that sensor for you and the healthy sensor, and tells you if something is going wrong. Then you can notice that discrepancy between the model and the real life component that is a sensor in this example. Good. So this is called analytical redundancy. And basically, fault-tolerant control drops under analytical redundancy because it uses the methods that they don't need necessarily the hardware redundancy. And we can have also the combination of hardware and analytical redundancies that we call it hybrid redundancy. All right, let's have a little bit closer look when we use these redundancy strategies for fault detection, for example. Well, on the top of this slide, you see that when we use redundant sensors in our system, we have hardware redundancy apparently, and then we can use the outputs from these redundant sensors as well as our main sensors, and then we develop a detection logic that basically it's a kind of voting scheme. If, let's say, majority of your sensors for the same performance parameter is telling you that, let's say, the performance should be this, then you go with that, right? You just take the majority as the legitimate information. And then you can detect and isolate that faulty sensor, for example. Well, you can just assume if, let's say, you use hardware redundancy for the actuators, how heavy and expensive would get your system, right? Particularly if it's an aerospace system, for example. All right, now let's have a look on the analytical redundancy. In the analytical redundancy, as you see, guys, instead of redundant sensors, we use process model of this system. Or instead of process model, you can use some form of knowledge, expert knowledge from the system. All right, okay. So depending on if you use process model or the expert knowledge of the system, then you can have either model-based FDD or data-driven FDD. That I will talk about these two in the coming slides. And using this information from your model or expert system, you can have actually a decision logic that compares the information from your actual sensors and also your model and determines, okay, if something is going wrong or not. And then you get default alarms. Great. Now let's have a look on these two categories of FDD, depending on which one you develop under analytical redundancy. All right. So just before I go forward, I would like to remind you that the model-based FDD1 can have different approaches. We may have residual-based approach that I will explain more in the coming slides. You may have also fault estimation approach, set membership approach that basically these are more advanced topics. I leave it, if you need, you can write to me. I give you good references for that. In the data-driven FDD, we do the analysis in time domain, frequency domain, and time frequency domain. So if we have a look on the basically data-driven fault diagnosis and lifetime prognosis, this analysis that I said, time domain, frequency domain, and time frequency domain, is a part that is the core of this, this method. And you start from the signals that are obtained from your sensors. They are raw signals. And then you need to pre-process these signals. You need to filter them because they are too noisy. You need to amplify them because they are too small in magnitude, and so on. And then you get more clean signals and use them for signal feature selection, extraction using time domain, frequency domain, time frequency domain analysis. We call it data analysis. And that's why we say it's a data-driven method, because it works with data analysis. And lastly, you use artificial intelligence, a very hot topic of today that you apparently, I assume all of you have heard of, and or statistical approach. Different approaches are available for you that you can develop the condition classification, meaning if something is classified under fault or like under normal situation, or regression, that you can get a time-dependent behavior of the system in the normal case, and then do the residual generation and so on. All right, so this is the data-driven approach. What is the, just before going forward, if you're interested in this area, you may refer also to this recent paper, review paper, that is that gives you a lot of information, useful information, and it is written in a very very how do you say, reader-friendly way. So it is easy to follow the topic, and also very easy and straightforward diagrams and figures. So I think you can have good information there. If you're interested, you can refer to there, and it is free to check it out. Well, the model-based approach, as it is shown here, if we talk about FDD1, it looks like this. And it uses actually the plant nominal model that mostly it is a mathematical model of the system. And it is analytically developed, and basically it estimates the normal behavior of your model using the information from input and output of the plant, right? Well, so this information, when it is used in the model, gives you the estimation of the normal behavior, and then you compare that with the actually real-time behavior. So real-time behavior compared to the model estimation. There, it gives you the errors, those errors that at the beginning of lecture I mentioned, and we call them residuals, like by technical term. And these residuals can be evaluated by threshold testing. For example, the residuals ideally should stay 0 if the system is healthy, and they just deviate from 0 after fault happens, and then you just, if they pass a threshold, a specific value that you determine already, then you can say, okay, fault has happened, and the FDD information is generated. All right, so FDD information then can be used for prognosis as well. And in the model-based prognosis, as you see here, guys, we use the plant degradation model instead of nominal model. And this is very challenging because you need to develop a model that gives you the estimation about the future behavior of the system. So you're working with future information, and that makes it very challenging. And you need to not only use the FDD information, but also the expected future operating conditions of the system. If it is a wind turbine and it is going to winter time, we need to take this information also as a kind of useful information for the plant degradation estimations. Well, since it is all about future, we need to, and it's an uncertain environment, we need to use appropriate uncertainty management and model parameter updates as well, because we need to constantly update the parameters of this model depending on these input informations. And you can use, let's say, particle filtering algorithm as a useful algorithm for these two parts. Well, let's keep it at this level, because I don't want to enter all details of this, as it is more advanced, and you can just refer to the references if you're interested. Okay, now having all this information, we can get to the fault-tolerant control. What is fault-tolerant control? I would like to maybe read this part, because it is coming from this useful reference from my former PhD supervisor, actually. It is a very useful reference. I would suggest everyone interested in this topic to have a look on this reference paper and learns about this more. Well, fault-tolerant control is a control system that possesses the ability to accommodate the system component faults or failures. These system component faults or failures can be sensor fault, actuator fault, or process faults. And automatically does this function, meaning accommodating these faults, and is capable of maintaining the overall system stability and does this in an acceptable way. So in other words, you take on a graceful degradation in the performance, but still you let the system continue working in a safe manner. All right. So you do this like we call it accommodation, as I already explained. Well, FTC or fault-tolerant control can be developed either in passive approach or active approach. Passive approach is a sort of robust control. So if you just Google robust control, you find many references. Those types of controls that they are robust to some levels of faults, okay? And they don't need FDD information. So regardless of FDD information, they are robust to some levels of faults. These are passive FTC systems. And active ones are those that they use the information from FDD that I already explained. And in the future, also LTP, right? This useful information can be used in control to actually enable some control reconfigurations. And depending on how you implement this method, you can have either online controller redesign approach, meaning that after your fault is detected and identified, you calculate new controller parameters in real time. So you can assume how challenging it is. And then the new controller can be redesigned in online condition and can accommodate default effects. The other method that you can use is offline controller pre-design approach, meaning that you already do some design. Let's say you design 3 PID controllers for 3 actuator effectiveness. If your actuator is fully effective, you have PID controller 1. If it is 50% effective, PID controller 2. If it is 25% effective, PID controller 3. And then, depending on FDD information, you select between these control, pre-designed control systems, okay? So it is less challenging compared to online controller redesign approach. All right, keep your questions in case we come back and explain more on this. Okay, so here we have one sketch from active fault-tolerant control. As you see, the main important factor that distinguish this approach from passive is using FDD system. So you have to use FDD information to enable reconfiguration of your control system. And when I say reconfiguration, meaning that redesign of the controller or pre-selection between the pre-designed controllers. And this reconfiguration, as you see, guys, it not only can change the control system's algorithm, but also the command to the system. Because when the system becomes faulty, you cannot expect a faulty system to be fully active. You cannot expect, let's say, an engine that gives you full power when it is faulty. So you need to sometimes revise or modify the command that you have for the system as well. You reduce the demand, right? Depending on the FDD information. So that's the idea of actually this branch that you see here. All right, and what is the passive one? Passive one actually, just as I mentioned, it's a kind of robust control. You don't use any information from FDD. So it can be designed easier. However, it has limited fault tolerance capabilities compared to the active one, okay? So it's a kind of trade-off. You need to compromise between your design difficulties and the actually level of fault tolerance that you can expect. Okay, now let's have some examples, okay? All right, for the examples, actually, I am going to go over a few simple examples just to give you some ideas, right? We don't want to go in the last lecture of your course into too much mathematical details. Well, you remember the residual-based FDD system that I already showed, and there you saw that the heart of this system is basically the plant nominal model. And if you design this nominal model using Takagi-Sugeno fuzzy models, that is a specific method. I will show you how it works. Then you can have a nominal model for your plant. And then you can get that estimation, residual generation, and residual evaluation afterwards. What is TS fuzzy modeling? TS fuzzy modeling is can be explained in this slide very briefly. Without loss of generality for a single input, single output system, we can represent the system using this expression that you see here. And basically, phi vector that you see here is an information data vector, the past information of the system, outputs and inputs of the system, and ny and u refer to the model order. And also, you have to accept a modeling error because it's impossible that your model being perfect, right, in real life. Now, the challenge and the problem is to approximate this f that is actually a nonlinear function. And then it can give us the output that we expect, the estimation that we want from our nominal model. In TS fuzzy modeling, we approximate this f using m rules. And these rules, each of them represent a linear approximation of the system, right? So as you see, it has some parameters in it. And these parameters can be determined like by system identification, nonlinear system identification. We don't want to enter too much details. Just keep in mind that you approximate this f using m set of rules. And then each rule has a contribution to the output of the model. So you need to take a weighted average over the rule contributions, and you get the output of your system. That is actually the nominal model inside your FDD system. Okay, now using this approach that I explained, I'm going to show you how we can do the FDD of blade pitch system in a wind turbine. It's a very common and important severe case, and it causes millions of dollars of loss in large wind farms every year. So it's very important that we detect the pitch sensor and actuator faults in the pitch systems of your wind turbine. Okay, there are two designs shown here just to give you an idea how it works. The first design is coming from first paper. Second one is more advanced for the same problem from the second paper. Of course, they are like just a part of the solutions in those papers. Just I want to show you how FDD works. So here, as you see, guys, we have blade pitch actuation model that basically you have I equal 1, 2, 3. So meaning that blade 1, blade 2, blade 3. So to the number of blades, we have actually models. And we use appropriate input features from the wind turbine. And then using that TS fuzzy modeling, we approximate the blade pitch angle, right? So we call it estimated pitch angle. We can compare it with the measured pitch angle. Because whatever these faults that happen in the pitch system, it changes the measured pitch angle. So if you compare it to the nominal pitch angle estimated from your model, then you can get those errors or residuals. And then you evaluate it using threshold testing, for example, and you can get the detection signal that's a binary signal. It can be either 0 or 1. If it's 1, it means there is fault. If it's 0, it's just like the system is healthy. And of course, you can get the fault estimation, that is the information of fault diagnosis, right? If we had only this one, it would be fault detection. But since we also get the isolate the fault between the blade pitch angles and also the magnitude of fault, we have the estimation. Well, the second approach is, as I said, its second design is similar, just with less number of inputs. Okay, so the second method, I'm gonna show you the results after this example altogether. So the second example that I have for you is FDD of generator converter system. So this is the generator of the wind turbine. It can get faulty and the probable fault is actuator fault in this system. Well, you can again develop a residual based FDD system for this purpose because this fault affects the measured output power from your turbine. Therefore, you can compare that with the estimated output power from a model of the system. And this nominal model, the estimated output and comparison with the measured output gives you the residual. And then you evaluate the residual, you get detection signal and identification signal. All right. Here we are, we have the results. As you see on the top, let's say on the bottom first we explain. So at the bottom, actually, you see the fault indicators that tells us, okay, when the fault has happened. As you see, during this period and this period we didn't have fault. Only during this period we had this fault, and we could detect it. Similarly for here, right? So on the left, we have the results for torque actuator fault in the generator, and on the right-hand side, we have blade pitch sensor fault detection results. And on the top here, you see during the faulty situation, you can estimate the value of the fault as well, how much fault we have. Let's say in the case of pitch sensor fault, we have actually this estimation in terms of degrees, but in the case of estimated torque, we have it in terms of Newton meter, that is actually the torque offset. And these are the detection times. So you see that in less than a second, we could detect these two faults. Okay, now the last case study that I have is FTC at individual wind turbine. Well, I give you two examples. The first example is FTC of blade pitch actuators with sensor faults. So remember, guys, we just explained how to detect these sensor faults in a pitch system. Now, when this sensor fault happens in the pitch system, since the pitch system, each of these systems that you see here, is a closed loop system like this, and it has its internal controller, when the pitch sensor fault happens, it not only affects the output measured pitch angle, but also it affects the overall actuation of the pitch angles of your turbine, because it propagates through this closed loop. So you need to accommodate these fault effects. And as you see here, if the FDD system gives us the information of this fault, including detection time and also the identification of the amount of fault, then you can accommodate the fault effects by correcting actually the measurement and the command that goes to your pitch system. Okay, this is your control command. Good. And you see here on the plot how it looks like, because the effects of this fault can be evaluated on the measured generator speed of the turbine. And as you see in the red case, this denotes actually the faulty operation without FTC. So if you don't use these corrections that I showed here, and sometimes we call it fault hiding the fault effects or accommodating the fault effects by these corrections. So if you don't use that, then you're gonna deviate from the normal behavior that you have. And the fault happens, just for your information, happens, I think, I'm not sure, okay, here, 170 to 230 seconds. So anyways, if you use the accommodation, you can accommodate these effects and you can follow the blue reference performance that you expect in the healthy condition, right? So the green operation shows the operation with FTC that is actually implemented here by the automatic signal correction strategy. All right, the second example and last example, I hope you're not tired, is actually the FTC of generator converter with torque actuator faults. Well, torque actuator faults is again the fault that we already explained how to detect it, but here I'm going to show you one example that is passive FTC, meaning that we don't use FDD information in this method. Well, when this fault happens, it changes the generator output power. So the measured generator output will be changed by the fault effects. And if we compare that with the nominal actually information, then we can actually have the error, plant error, right? And the plant error gives you the error information that is the symptoms of the faults, basically. So when your system becomes faulty, this error becomes a considerable amount. Otherwise, it's just due to disturbances and noises in the system, and it's a very tiny amount. All right, so we use this error information as well as the change in error information, the derivative of it, and we actually adjust some tunable parameters inside our torque controller that controls the generator power. Well, these are the equations of this controller, and the red parameters are those like constant parameters in normal wind turbine, in like conventional wind turbine. But here we make them adjustable parameters, meaning that we can tune these two parameters between these two ranges and over these two linear transformations. And different strategies you can use, different methods you can use. Here we have used, let's say, fuzzy adaptation mechanism. And the fuzzy adaptation mechanism uses different rules. And these rules actually give you the real-time information for these red values that you see here, right? And it adjusts these values actually depending on the error and change in error that you have. Good. So this way you can, of course, these are the membership functions. We don't want to enter all details of this method, but this mechanism helps you to adjust the parameters of this torque controller and depending on the fault severity, and then you can accommodate the fault effects. And here you need also a reference dynamic model because it's called model reference adaptive control, but you don't need the detection time of the system because apparently you don't, it's a passive way and it does this accommodation like in real time. For healthy system, the errors are very little, so this accommodation is almost zero. But for the faulty case, the accommodation and adjustment of the torque parameters becomes considerable. Okay, the results that you see here, guys, it's important you see that the wind speed that we have used for the evaluation looks like this. There are 3 different wind speed profiles that we have used, but the results only for the blue one is given at the bottom. You see generator powers. So the turbine is a 5 megawatt turbine and is generating 5 megawatts of power. And during this period of time, 495 to 520 seconds, we have that actuator fault. And if you don't use that method that I explained, your power would be over generation, and that would be dangerous for the turbine because it needs to generate only 5 megawatts, not more than that. But if you, let's say on the left-hand side, you see the amount of fault is 1000 Newton meter torque actuator offset. And on the right-hand side, if I increase this amount of fault to 2000, meaning doubling the fault severity, you still can accommodate the fault effects as you see with the green color compared to the blue. But unfortunately, as you see, guys, it's not as good as the left-hand side picture because the reason is that the solution that I explained is a passive solution. So passive FDC is not as strong as active FDC in terms of fault accommodation. However, it is simpler to design. It doesn't need FDD. Okay. Now, I am almost done. This is the last slide that we have, and it is some remarks that I would like to just wrap up this lecture with. The first one is that engineering of safety critical systems is a complex task. What does it mean? It means that actually, if you want to really develop a FDD system, a useful and effective FDD system, FTC approach and actually controller, you need to really understand this system. And normally these systems, since they are very complex, it spans different technical fields. So let's say if you're working on wind turbine fault diagnosis and fault tolerant control, you need to understand electrical part, you need to understand mechanical part. So you need to really, really equip yourself with good knowledge, right? The second point is that the control problem, apparently you can say that, actually I think it's safe now that we say that control problem for safety critical systems should be designed under both fault-free and faulty conditions, meaning you shouldn't just suffice to conventional controllers. You need to really go beyond and develop fault-tolerant control as well for these systems because they are very safety critical. Well, the third point that I have here is the significance of FMEA. You can say that when you are going to address a fault, you need to really understand that fault completely and know what kind of monitoring system, what kind of redundancy, it's the best solution for that. So a comprehensive and meaningful FMEA is really important for us. Well, FMEA determines different kinds of faults for us in the system and pinpoints many different faults. You remember that list based on severity. So depending on the fault, you may need to consider active or passive methods. So some faults may be okay just with the passive controller to be accommodated. Some others may need active solutions, right? So you need to really pay attention to this, and you need to be flexible in using your available tools. Well, the other point is about model-based FTD. Model-based FTD, guys, can be useful not only for control FTC, but also for condition monitoring purpose. So it is very important, and that's why the research in this area is also going more towards model-based FTD, because the information from FTD systems with model-based approach can be used not only for condition monitoring, but also for active FTC. And last but not least is prognosis. As I briefly pointed out before, prognosis is a very, very important component in the health management of a safety critical system. And unfortunately, it is not studied completely because of its challenging nature. However, it is very important component because it really enables us for effective condition-based maintenance and planning of the maintenance and service. So I would suggest, if you are going to continue this field of study, definitely have a closer look on prognosis and help this area of research in this aspect as well. All right, with that said, I am done with the lecture, and I open the floor for questions. Thank you very much.
Thank you very much, Hamed. Really interesting what you have presented. For sure, everyone is amazed because it's a bunch of information and it's a huge field with many opportunities of specialization and application areas. I don't know if any of you have any question for Hamed, please feel free to open your microphone and ask, please.
Thank you, Ismail.
Okay, in the meantime, if anyone, I have a couple of questions that are really simple, actually, general questions about the topic. I have also, just for your knowledge of everyone, I also have worked much briefly than Hamed, of course. Hamed's an authority in this field, in this particular area. And one of the challenges that I have found in applying these approaches is the modifications that a system, overall the software modification that a system has to pass through in order to accommodate or to accurately adapt these approaches. So in your opinion, Hamed, how easy or hard is to integrate these approaches in common control systems installed on everyday machines?
Well, very good question, actually. Yeah, it is basically, that's the challenging part, because using these methods in theory, it's like, even though it is still challenging, but there are more possibilities to like show their effectiveness in theory and in simulations and stuff like that. But in real life applications, when we are going to really develop and implement the FTC solutions for real life plants, that's very, very critical in the industry, because for industry, and that's why you see that FTD fault diagnosis, it's much more developed in industry, and they have adopted these solutions. But when it comes to FTC, it's like it's not that adopted because of the fact that you need to really do the reconfiguration of this the controller when the fault happens in the system, and that means that you need to really make sure that the system nothing would go wrong, you know. And when it comes to a real life plants, validating this situation would need a lot of efforts, and at the same time a kind of very systematic and well-supported infrastructure that you can really validate these solutions and make sure that, okay, if I use a FTC system that changes, redesign my controller on a wind turbine, for example, in a real life scenario, nothing would go wrong, you know, because as I said, defaults definitely happen in the lifetime of the system, but they are not all the time. So you need to, as a kind of operator of the system, you need to make sure that, okay, this solution that I'm adopting for my system wouldn't cause any troubles in the case that the system is working healthy. So that's the issue. And I hope I answered your question.
Yeah, definitely. And also, since this is a really open area with a lot of opportunities of cooperating and also a lot of challenges, I understand that data-driven models are part of the future, because everything is kind of connected. Now we have at least any of us has at least the computer and the cell phone connected to the internet, and something similar is happening in machines. So we have sensors everywhere, and through IoT or Internet of Things or industrial Internet of Things solutions are able to habilitate this monitoring for generating useful databases for data-driven modeling. But also this, unfortunately, as everything, provides like a leak for control systems. You didn't mention, but also you are working in this area. It is kind of related, which is related with cyber attacks. So right. I don't know if you can briefly just give a glimpse about it in this context.
Yeah. Sure. Thank you very much for actually bringing up this point, because I wanted to talk about this, and I was telling myself, wish I was going to this last slide actually, and it's a good reason to go now. Well, yeah, the thing is that I don't know how much your students are familiar with the concept of Industry 4 and Industry 5 revolutions. These two revolutions in nowadays systems, actually, they are making the systems more digitalized, more like intelligent and interconnected. For example, just again, I give example in wind energy, but wind turbines are becoming more digitalized. They can communicate with each other and tell, okay, how much wind speed is received by, let's say, this turbine, and the other turbines would know, okay, how would be the wake effect behind that turbine in front of them, and so on. So this digitalization of the systems is, as you mentioned correctly, is making a lot of data, and apparently that would be useful because it gives you good tools using AI, let's say, that you can develop more effective solutions for FTD, for LTP, and also FTC potentially. But the problem is that it comes with vulnerabilities to cyber threats. And as you see in this slide, let's say, because of this vulnerability to cyber attacks and threats, we have to actually expand the solutions that we talked about. And let's say instead of FTD alone, nowadays we call actually detection and identification of faults and attacks. So you need to add this parameter or factor of attacks as well into your considerations, because you cannot rely on the fact that, okay, my system, my solution that I developed for FTD would work all the time, because maybe those inputs information that you use for your FTD, they become compromised by adversaries, right? So, and this happened, right? Let's say just in last March, if I'm not mistaken, 11 gigawatt wind energy in Germany got completely shut down because of a cyber attack. And that is like something that is getting more and more unfortunately frequent nowadays. So that's the thing that you need to consider, this as mentioned in this box. And also, when we are talking about fault tolerant, apparently, again, we need to also consider the factor of attacks as well. So nowadays we can expand these terminologies to fault tolerant, attack resilient control as well. And more or less, the methods that you use for detection of faults and attacks, can be more or less similar. At this level, if you assume that there is a successful attack that bypasses the traditional cyber defense technologies like I don't know, like firewalls and so on, then those attacks, those successful attacks, have to be handled at the control level. So then the methods that we talked about and we studied for fault detection, diagnosis, and fault tolerant control, to some extent can be actually expanded to detect and accommodate the effects of attacks as well. However, the challenging part would be isolation between faults and attacks, because even though you can detect the attacks as well as faults, I mean, ideally, if you can do that, how you can isolate these two, because that's important. Because if you cannot say, okay, something went wrong in my system, I could detect it. But if I cannot say if it's due to a fault or if it's due to an attack, that would be a problem, because I cannot recover my system completely, because I don't know those like intrusions in the system if they remain open to the adversary. So I need to really find the ways that I can isolate these two as well. So that's a real challenge. However, the point is that, as you mentioned, we need to expand this field of research to attacks as well as faults if we are going to really embrace that information from more digitalized systems. Yeah, that's what I wanted to say.
Excellent. Thank you very much, Hamed. I think Farid has a question, so please go on, Farid.
Thanks, Ismail. I do have two questions. The first one goes on the same line that the first question Ismail asked, and that's how does one determine the maturity of a given approach of failure-tolerant control or detection? I mean, one can just give a proposal and then say, okay, this is ready for just development phase and with certain constraints, or it's ready for production, that's the first question.
Okay, just I repeat this question in case if I couldn't understand correctly. What you are asking is about like the implementation phase, right? Let's say you have developed an FTC solution. Now you want to like convince the industry that adopts that. Is it
not necessarily convince the industry or the client, but more on, okay, how do I show or quantify that my approach has enough maturity to be ready for a production system?
Okay. At the level of at least your own like validation and verification. Okay. There are different methods, but let's say just like bring this slide that I explain on. For example, let's say you develop FTC solution and you get something like this, some results like this. This is first level. If you get these results, that's good. It shows that things are working, right? Because you could accommodate default effects and you can say, okay, I could do this. But the second step that you have to go through is like what we call is Monte Carlo simulations, meaning that you need to really make some like random variations in the input features that you use in your FTC and FTD systems, and therefore you actually can rerun the simulations for, let's say, 100 times with like random variations in those signals, and then you again verify that you get same kind of effectiveness in terms of fault tolerance and results from FTD. So if you could do that, then, and you would still get good results, then you are safe to say, at least at the level of research level, you can say, okay, I could prove that my solutions are effective, right? But if we go towards one step ahead, like industry, again, that would be a different story. I think it would be much more difficult to convince industry, because as I said, it needs like real life validations, and that would sometimes not easy. on real life systems.
Okay, thank you. Yeah, it makes sense. I think so. In general, it's
And
having
just
lots of data.
Yeah, sorry to interrupt you, but if you refer to this paper, I have explained the validation part that I showed how, let's say, I designed, or better to say, formulated a kind of Monte Carlo simulation strategy that you can verify the solutions in a more sensible way. Yeah.
Okay, thank you very much for the answer.
You're welcome.
The second question, unless someone else wants to interrupt me and throw a question, that should be fine. The second question is, so you mentioned AI in your presentation, and I wouldn't be surprised that this area of research has run into AI-based models or whatever topic. So how do you assess the, not sure how advanced research in this field is in terms combined with AI. I'm just using AI as a general term, but how do you assess the reliability of an AI-based either failure detection or failure tolerant control compared to a more conservative and perhaps deterministic approach?
Good question. Yeah, well, that is actually more or less the same kind of approach, but might be more challenging, I would say, because depending on your AI solution that you develop, sometimes it's very time-consuming to repeat and make sure that like 100 times again you do like evaluation on your AI-based system. So that might be more challenging, but still, I would say more or less the same. You need to make sure that your system is like under at least the like conditions around the conditions that are targeted for design of the system is reliable, right? So let's say if it's about FDD, fault detection diagnosis, the number of like misdetections, the number of like missed identifications, these kinds of things during a multiple amount of simulations or like experiments have to be really counted and shown that it is reliable. So it's still more or less the same, but I would say it might be more challenging depending on a specific solution that you developed.
Thank you.
You're welcome.
Thank you very much, Ahmed. I don't know if anyone has another question. Otherwise, we don't want to abuse your time. Thank you very much, Ahmed. It's been a tremendously interesting topic. And thank you once again for accepting our invitation for this last. I think we have one more question. Please allow Eric to, please go ahead, Eric.
Hello, thank you. Thank you, Ahmed, for the presentation, for showing us some of your work and area of study. I wanted to ask what inspired you to focus on this group of study and professional research? What was the thing like you like the most, or?
What I like the most?
Yes, like I want to know like what was your process of saying, okay, I like this. I'm going to focus on this, you know?
Yeah, actually, very nice question. Basically, I was firstly working on conventional control, right? Like normal systems without faults. But the way that I got interested in fault-tolerant control I would say it was more coming from detection diagnosis aspect, because I knew that it's like particularly my background was on engine control. So I knew that, okay, the faults, the problem of faults and how much they are important in such application. So because of that, I got like interested to know more about detection. And then when I understood, okay, the value of fault detection information for control and how much you can actually enable your system to work like longer just by using that information to leverage control, that got me more interested in FTC as well. And the reason that I moved also from engine systems to like turbine systems, like I mean wind turbines, is that basically the wind turbines, again, I mentioned maybe briefly during my presentation, they are excellent in terms of like studying the this field, because they have a wide variety of faults in themselves, and they are really like systems operating in very uncertain situations. So this field of study can be very well like demonstrated in that application, I would say. So that's why I got really also interested in that, and I continued, and then I continued, you know. So yeah, it's like this. But that's an interesting field, I think.
Okay.
Thanks for your question.
Thank you.
Yeah, just before maybe I wanted just to point out another point, maybe related to Farid's question. Just I remembered, maybe it can be useful. It's related to the fact that when you are using AI, you need to also make sure how you develop your, let's say, regression models or classification models in general, because like the way that you use that data, you know, for testing, for training, how much data and what combination of data you use for testing compared to training and so on. That's very also important. So I would say before it gets to the like validation, that is like something that you need to really, and there are like works on that. And particularly when you want to use AI, let's say for prognosis, that would be even more challenging depending on, let's say, data that is available to you. Because normally this data is mostly the data that we have, let's say, at least for wind turbines, I can say, they are mostly like normal data. So you cannot have those degradation information in them, like at least labeled information. So that would be something that makes a lot of trouble normally in real life solutions when you are developing. So yeah, that is also some other point that comes to my mind.
Thank you.
You're welcome.
Okay, I think we can finish here. Thank you very much once again, Ahmed, for
You're welcome. My pleasure.
lecturing us.
Thank you. Thank you very much for invitation. It was great being with you guys. It's and I'm happy that it was the last session of this course. Finishing with this, it's very interesting. That's I take it as a good luck for everyone. Also.
Thank you very much, Ahmed, and thank you everyone for assisting to this lecture. We will see you next week in the presentation of the project. So goodbye by now.
Sure.
Thank you very much.
Bye-bye. Have a good evening. Bye, guys. Bye.